So in the previous two sections, we introduced two different sampling techniques, the temperature scaling and the top case sampling. Now we are going to combine those two to update our generate text simple function that we used earlier in chapter 5 to generate the next token. So let's go to our previous chapters.py file. And here we have this generate text simple function, which we originally implemented in chapter 4. And we are going to modify it step by step for temperature scaling and top case sampling. So right now it's just doing the greedy sampling, always generating the most likely token. But yeah, we want to add some randomness and sampling to it. So let me copy this here first, and then I will modify it step by step. So let me also get rid of some of the text here, because then we can fit more code into this window. Then it's easier to read and see what's going on. And so one thing I'm going to do first is I'm adding a few arguments here. I will add, let's say, the temperature. And we can't divide a number by 0. So this, if we have logits divided by temperature and the temperature is 0, this will fail. But I will add a if condition in a few moments. So the temperature scaling gets skipped if the temperature is 0, so that the 0 allows us to say basically we don't want to randomly sample. Then let's do top k, and we can also set a default parameter. Let's do none. And one more thing I want to introduce right now is the end of sequence ID token. So we are not really needing it right now. This will be a concept end of sequence token that we will be revisiting in chapter 7. So in chapter 7, we are going to instruction fine-tune the LLM to give us answers to certain questions. And then part of this procedure is also teaching the LLM when to stop generating the answer. And for that, we will be using the end of sequence token ID. And as I mentioned before, I kept this book relatively efficient. So we are going to reuse this generate text simple, or the new generate text simple function, later in chapter 7. So I'm already adding it here so that we don't have to redefine it later. And just to briefly explain what I mean by end of sequence token. So EOS stands for end of sequence. So if we have the tokenizer, it has a certain vocab size, in our case 50,257. And the last token here in this particular tokenizer is the end of sequence token. So we can double check this, and I can do, because Python has 0 indexing, so I'm going back by 1 position. So I can also just type 6. So this should give me this end of text token. So this one corresponds to this, or we can use this as the end of sequence token to tell the LLM or our generate function when to stop generating text. So what we could do is, for example, we can say if end of sequence ID, or you can maybe do it like this, it's more intuitive. If our next token equals the end of sequence token ID, then we break, so we don't generate more tokens. And why is that useful? For example, there might be a question, I mean, we have the max new tokens, but there might be a question that only requires a shorter answer than we have defined in max new tokens. So we save space. So for example, trivial example, we ask our LLM to answer the question, what is 2 plus 2? The answer is 4. So even if we have 25 tokens, we don't need 24 more tokens to answer the question. We can just, stop generating after this short answer. And so using an end of sequence token ID and teaching the LLM when to use it, we can get shorter answer and save time and money in that sense. So this is just something we will be revisiting later in chapter 7, but I will just have it here already. So for reuse. And so let me now add temperature. Maybe let's do top k first. So we say if top k is not none, then do something. And then we can also do, let me just have some placeholder code. If temperature is greater than 0, then do something. And else do, one of these days I will get used to this keyboard here. Slightly different from the position that I'm used to, so I'm always making these typos here. So what we have here is we use top case sampling if we have a value, for example, 2, 3, 4, 5, 6. we use temperature scaling if the temperature is greater than 0, and otherwise we use our procedure as we have used it before. So let's fill in the blanks. Let's do the top K maybe first. So we can copy the code from the previous section. Can just fill this in here. I see I have to make one modifications because the last or the next token logits are now just called logits. So we'll have to make sure this uses the same variable name. And then here, this one, we'll copy this one here. Okay, and the same thing, we have to make sure we use the same variable names here. Okay, and I think because there's one more dimension, we also have to make sure we get this correct here. This looks okay to me. Okay, we are not doing any softmax because we're going to use the softmax here in the temperature scaling, because the way the function is set up, if the temperature is 0, there is no randomness, there will be an argmax. So we don't need to do anything here. We will take care of this in the temperature scaling scope. So let's apply the temperature scaling. And then we need, of course, the torch.softmax to get the probabilities. What else? Yeah, and then we need the multinomial, right? Multinomial, and we give it the probabilities. And I think we only want one sample, not many samples. So I think if I see it correctly, this should work. So what we do is we do the temperature scaling if the temperature is greater than 0, and then also if there's a top case scaling happening, that is also used, because this will do the -infinity, and then we do the temperature scaling. If the temperature is 0 though, then it will use torch argmax, so it will be deterministic. So what that means is by default, it will behave similar to what we had before. So let me maybe just see where we had, well, I can just define it below here. So I wanted to just show you the default behavior. Let's actually rename this, because it's not the simple text generation function anymore. It's slightly more sophisticated so that we can tell them apart. And then let me actually just copy it from here. Let me show you how it works. So let me comment this maybe out for now. And so this should work similar to what we had before if we use the default for top K, which is none, and the temperature of 0.0, because then this code won't get executed, and then it will behave similar to what we had before. So this should be, yeah, deterministic behavior. And then if we add the top K and temperature scaling, we get a different response. So here, this is essentially now combining our sampling strategies, but as you might see, this is still not really making sense at all. This is just some gobbledygook, so it's gibberish almost. I mean, there are words that make some sense. So to work on surprise, us had gone with random. It's relatively random still. And this is not because our function here is bad. It's really that we have not trained the model much. You know, that little training on that one little book, it doesn't do that much really if we ask it sometimes questions. So don't worry about it yet. We don't really want to spend thousands of dollars on training. We will be actually at the end of the chapter load the pre-trained weights from OpenAI, and then later in chapter 6 and 7 we will do actually more training that does actually something useful. But for the base model, for the pre-trained model, yeah, you can't expect much from training for 5 minutes on some simple text. So for that, don't worry about it. We will be loading pre-trained weights into our architecture so that we have a solid model to work on in chapter 6 and 7. But yeah, we will be reusing this function, because I will show you once we have good model weights, this function will actually work quite well. And yeah, and so by the way, how did I determine these numbers? I just put in some numbers, but in reality, when you use the model, the model usually comes with a model card where the developers of the model, they suggest some settings for top K, top P, and temperature scaling. So if you follow the new models like Llama and everything, they do come with suggestions, and it's usually a good idea to use these suggestions. But now that you know what temperature scaling means and how it works, you know that you can actually increase the temperature to increase the randomness and decrease the temperature to reduce the randomness. And that was, this was mainly the goal here in this lecture, to explain a bit what these methods do. And once we have a better model, once we have loaded the pre-trained model, let's actually revisit this and play around with this and see what we can generate with slightly better model weights.
Get this book at manning.com